Okay. So we want to continue then with pipe networks. It's still kind of yellow, isn't it? Just on my screen. Okay, so a couple of new concepts that we want to add to pipe networks, and then we'll work an example. So we're going to call this networks part 2, if you will. First off, a little bit of review. If I did a pipe network, and it's really simple here. So I'm not going to put the nodes and stuff on there, but let's assume that I had a reservoir coming into this pipe network down here on this node. Okay. And of course, there's flow going out, but that's the only inflow that's occurring. We talked about in the class about fixed grade nodes, and reservoirs are fixed grade nodes. In other words, they have a hydraulic grade line for a steady state analysis. But I'm trying to figure out how to frame this. This reservoir supplies the pipe network, okay? If I know, I guess I better notate some of these, A, B, and C. If I know that my demand Q sub A is there, Q sub B is over here, and Q sub C is over here, do I know how much flow is coming from that reservoir? So the question is the flow from reservoir. So Q sub A is known, Q sub B is known, Q sub C is known. Do I know the flow from the reservoir? And yeah, so you're shaking your head, yes, we do know. So what would be any different if I, rather than just did a reservoir right there, I just put an inflow, Q in, and solved this pipe network? Can you think of what might be a little different, or is anything going to be different? Are the flow rates going to be different? Right, so the flow rates are the same. Okay, well, how would things be different? You know, if I called A option, option A was QN, option B was this reservoir right there, and I didn't leave myself enough room, but I'm going to draw a line out here. And what if I had a reservoir that was really tall? And this is option C. How would the flow be different between any one of those? And the answer is no different, right? Because the flow rate going out is still the same thing. I can't shove more flow in my network just because I have more pressure or a bigger reservoir at the inlet side. But what does that change? What would that change within my pipe network if I went from a small little reservoir here to a great big deep reservoir?
Your minor losses.
Okay, so we've got two things here, HGL and minor losses. So let's deal with minor losses first, Aaron, and I appreciate the comment. But minor losses are a function of what? What determines the minor loss? The minor loss coefficient and the flow rate, the velocity. Okay, the flow rate, which determines the velocity. And if the flow doesn't change, then the minor losses don't change, because the flow doesn't change, right? And our minor loss coefficients don't change because physically we haven't changed anything about the geometry of our system. We haven't added any more elbows, anything like that. So we can say that the hydraulic or the minor losses are the same. Laura, you said the hydraulic grade line changes. And that is absolutely correct, because now I'm starting with a known hydraulic grade line that is higher than there. So in a real world common day language, what does that change in my network? Hydraulic grade line is higher. Hydraulic grade line is made up of the pressure head and the elevation head. I haven't changed the elevation head in my system because it's a physical system. The location of those pipelines are the same, but the pressure now has changed. So when I turn my faucet on, I'm going to get the same flow rate. Actually, the flow rate is set by the demands. And I know your mind's like, wait, if I push it on, I'm going to get more flow. Well, yeah, now you're talking about something different. Now you're talking about change in the flow rate. But if I say the flow rate is set, then the pressure in my system doesn't change the flow rate. Okay, so this is kind of a chicken and egg type thing, and you need to say, okay, if I'm assuming the flow rates are set for whatever, however we're controlling the flow rate, if I assume the flow rates are set, then the pressure doesn't change the flow rates. But in reality, the pressure would change the flow rates if it's just a faucet you open up, because now more pressure is going to push out more flow, right? But in this scenario, nothing changes. So what I'm trying to highlight is that we went ahead and we figured out how to solve this system right here. For the flow rates, we've said nothing about solving for the pressures in the system. And at some point, we're going to want to know the pressures. So after we know the flow rates, can we solve for the pressures? Sure, we have to start at some known pressure, and then we just walk around our hydraulic grade lines, and we know the pressures everywhere after that. So we still have a second set of equations that we need to solve, but it's just plug and chug. It's just the energy equation from point A to point B. Solve that, then go to point C. Solve that, go to point D. You know, you just walk around and find the pressure at all those places because we already know the flow rates. Okay? It's like solving a truss back in statics. You know, you start with what you know, you go along one angle, and once you have that truss member figured out and the other connection, well, then you go to the next connection and you can walk through the whole truss. It's kind of like that. So we are going to come back to some known value to calculate the pressures in our system. But in this case here, where I only have one reservoir, I could replace that reservoir with Qn, and it would still be the same set of equations. Okay. So this is where we're going to get to part two now. There's two things that we need to add into this system of ours. And Aaron brought up that he said minor losses. Well, we haven't talked about minor losses yet. So let's talk about minor losses in the network. Okay, how do they fit into our calculations? You know, and this just popped in my head here, and I've never thought about this in the past, but when we do the three reservoir problem, we don't do minor losses on the three reservoir problem. But maybe we should, because if I added a valve on one of the pipelines going from the junction to the reservoir, what would I do? How would I change my equations if I did that? What would that do to the C value? It would increase it, right? We talked about back when we were doing single pipelines that minor loss, we could actually include it into the C value, and it just changes the C value. So minor losses in a network, they just change the C value. Recognizing that what C I'm talking about here is that coefficient that we created, that substitution, AKA CQ squared. Okay, that's all we have to do is include our minor losses in that value right there, and now they're part of our system. All right. So that one's pretty easy. You already know that. You just had to kind of formalize it here. The next one then is going to be what we call pseudo loops. Okay. Use if we have two or or more fixed grade junctions. And then we write energy equation between fixed grade junction, FGJ. Right? So you think back to the three reservoir problem, and we would write the energy equation from reservoir A to reservoir B. Well, reservoir A and B are fixed grade junctions. So we're actually going back to what we already know again. And A and C are fixed grade junctions. So we're going back again to that concept. So that's all we have to do in the pipe network now is add this pseudo loop. Now, why is it called a pseudo loop? Well, in pipe network vernacular, you know, in the terms that we use, the sum of the head losses around a loop equals 0. And some books like to say, well, if you go all the way around from reservoir A to reservoir B, and then draw this imaginary loop all the way back to A, that's a loop in of itself. And the sum of the head losses there have to equal 0 because you're coming back to B, all right? Now, I've found that students find that kind of confusing. And so I just go back to the three reservoir problem and just say, this is like the three reservoir problem. We're going to write from A to B. And we do that loop there, and we know what the energy has to be. A is known, B is known. We know where we start, we know where we end up, and those become part of the B vector of our matrix because those are known values, okay? But if you look into some texts, like I say, they'll do this whole loop and they'll do imaginary line coming back around. That's why it's called a pseudo loop. Pseudo meaning, for those that are not familiar with that word, not real. Okay, it just appears to be real, or it's kind of real, type of thing. All right. So what does this mean in practice? Another example here then. Okay, I'm going to just draw once again our favorite little pipe network here, two rectangles together. And I'm going to put then a reservoir out here on the left-hand side. And I'm going to put a reservoir out here on the right-hand side. And this is going to be reservoir A on the left and reservoir B on the right. I'm going to number my pipelines 1, 2, 3, 4, going out to that reservoir B, 5, 6, 7, 8, and 9. So in this case, I have 9 pipelines, 9 flow rates, and the associated junctions that I have with them. Put those as big circles on each of the junctions. So I know in this particular example that I would have, using a clockwise rotation, loop 1 and loop 2. And to be consistent, I'm going to stay with the same rotation of 1 and 2. And technically, we're kind of splitting hairs here. Technically, I don't think you'd have to, but you do have to be a little careful. So the safe thing to say is let's just be consistent. And we're going to do a loop starting at B, and that loop is going to come down here and end up at A. Okay. So imagine, if you will, you're standing on a block corner and you start walking down that block, and then you make a right and go down this other block, and then you make a left, and then you come way back 2 blocks, you know, make a left and come back to where you are. Does the elevation, you ended up back where you are, has the elevation changed? Not one bit, right? Doesn't change one bit. So my question for you is, does it matter how I go through my loops? Does it matter that I go 4, 3, 2, 1? Or could I do 4, 7, 9, 6, 2, 1? And would I still end up at the same hydraulic grade line back here today? Yeah, I would. I could do 4, 7, 9, 8, 5, 1. Now the reality is I have to go through pipe 4 and I have to go through pipe 1 no matter what I do. And that's a good thing because that's how I bring the flow rate from those 2 pipelines into my equation. They're built into the continuity equations at those 2 nodes, but they're not built into the energy equation. So the pseudo loop brings the connecting pipes from my 2 fixed grade nodes into my set of equations, and then will help me solve those 2 flows. But the path does not matter. What matters is that I get my sign correction correct. So I'm going to assume some directions on my flows, right? I'm going to assume that reservoir A is higher. I don't know, we'll put that at 2,000 or 200. The other one over here we'll put at 160. So I'm going to assume that reservoir A is feeding reservoir B. It doesn't have to be that way. It could be that A and B are feeding my whole system. Okay. But now I'm going to use the same logic that I use for loops. If I'm going to do this clockwise rotation for my pseudo loop, I would start off at the hydraulic grade line at B, and I'm going against the flow. So it would be plus C sub 4 times the absolute value Q sub 4 prime times Q sub 4, or Q sub 4 squared, right? And that takes me over to pipe 3, once again, still going against the hydraulic grade line. So using my sign convention of going against the hydraulic grade line is positive. So plus C sub 3 times the absolute value of Q sub 3 prime times Q sub 3. And remember, prime means the old value. I'm just writing this equation in the form that'll make it easy to stick into our spreadsheet. I could put just Q squared there. Perfectly fine, okay? It takes me now to pipe 2. So once again, going against it, plus C sub 2 times the absolute value of Q sub 2 prime times Q sub 2, plus C sub 1 times the absolute value Q sub 1 prime times Q sub 1. And when I get to A, that now has to equal the hydraulic grade line at A. It's not plus the hydraulic grade line. It's not minus, it equals the hydraulic grade line, because I have now arrived at A, and this is what the value has to be. And we're still doing steady state analysis. Remember, we're taking this snapshot in time that our reservoir is at this particular second with the demands that are going out the pipelines. That's what is static. My reservoir elevations are not changing yet. Once again, that's an unsteady analysis. We're not there yet, okay? Any questions about adding a pseudo loop to our system of equations?
What is this equation?
Okay, so that is the pseudo loop. Yeah, it's the energy equation going between our fixed grade nodes. Right? Gives us the pseudo loop. Why?
Can you define what you mean by fixed grade node exactly?
Okay, so fixed grade node, fixed grade means that the hydraulic grade line is fixed, and independent of the flow rate, that's what it is. So the hydraulic grade line, and this becomes a node in of itself, if you will, okay? And we don't treat it as a node, but those fixed grade nodes now define the pressure in my system. First, I find the flow rates because I'm using the flow equations. First, I find the flow rates. Then I can go back and find the pressures, and the pressures are dependent upon those fixed grade nodes. Okay, fixed grade, my hydraulic grade line is known at those locations. And that's why I can start at B and go to A and say that it equals A. Because A and B are known values, they are not unknown, they're fixed. And if you go back to that handout that we had, that I posted on Moodle, it said that P is equal to the number of loops plus the number of nodes plus the number of fixed grade nodes minus 1. If I remember that off my head correctly. Okay, so let's see if it holds true. 9 is equal to the number of loops, 3, plus the number of nodes, 1, 2, 3, 4, 5, 6. We're only counting the nodes of the pipes, not the reservoirs as nodes. But 6, did I do that right? It's not going to work out correctly. How come? Oh, because I can't include the loop. It's full loops. It's not the pseudo loop. Plus the fixed grade nodes minus 1. There we go. Yeah. So in the number of loops, we don't include the pseudo loop. That's built into the fixed grade node. Okay.
What does N stand for again?
Well, N stands for the number of nodes.
Oh, no.
Yeah, maybe use J. Did you use J in that report?
Yeah, we had used the J.
Okay, sorry. Yeah, J. All right. I should bring that up.
Okay, now let's.
Okay.
We have the J, L, and F.
The J and the what?
J, L, and F.
Okay, J, L, and F. Okay, great. So the number of junctions is 6. The number of loops, full loops, is 2. Fixed grade nodes is 2. So the number of pipes, which is the number of unknowns, everything matches there. This system is solvable. Okay, and this is the handout that I posted in Moodle from the faculty member at the University of Oklahoma that put together. Our book doesn't really cover this method too well.
I have a question.
Sure.
On the pseudo loop, direction wise, is it always just going against the flow rate? Or like you're moving?
No, so if I had assumed, Anthony, that the flow is coming from B and go in this direction, and also go in this direction, then these two terms right here, C sub 4 and C sub 3 would be negative because now I would be going with the direction that I assumed in the pipes.
But that's just based on like an assumption.
That's based on what, sorry?
Just an assumption.
Correct, correct. So just like in statics where we have to put direction to our force vectors that are unknown, in this problem, we have to put direction to the flow in the pipes, which is unknown. And then the numerics will solve that for us. It'll take care of it. It'll tell us if we got it wrong. Does that answer your question?
Yes, thank you.
Okay, you bet. Any other questions on this?
So the pseudo loop, is that always the kind of like the closest between the two reservoirs? Or could it be like around 7, 9, 8, 5?
Yeah, we can take any path we want.
Oh,
Now, I would prefer to take the shortest.
Yeah.
Because I'm lazy. But we can take any path we want to get there, but we need to go from B to A. We have to start at what we know and end at what we know. So yeah, I could go 7, 9, 6, 2, 1. I could go, well, 4 is on the front there. 4, 7, 9, 6, 2, 1.
okay.
And that would be perfectly fine to say, all right, I'm going to come down here and go up there and come here, and I'm still going to end up there. Or I could do the full thing and come back here and go down this way and go there. Either way, I end up at the same position and I'm going to get the same value. Okay?
So the pseudo loop equation is different if you run the other loop?
The equation would be different, but the values I'm solving for would be the same.
Oh, okay.
And if I had another reservoir on this, now typically we wouldn't have more than 2 reservoirs on something this small, but the potential exists that we could have another reservoir over here. Okay. Well, just like the 3 reservoir problem, now I can write a pseudo loop from C to B, following that clockwise rotation, or I could go from C to A, it wouldn't matter. Remember, I could go from A to B and then A to C, or I could go from A to B and then B to C. I get the same answer. Because everything is dependent, it's tied together. Okay?
But you wouldn't need to do C to A because it would be redundant.
Correct. If I did B to C, I would not do C to A because then, yeah, it would be redundant. And that would give me one additional equation that wouldn't do me any good. All right. Okay. So, sorry, I should have announced this. I did post a spreadsheet on Moodle. I thought I posted this handout, but I forgot that Moodle only shows one file at a time. So I can fix that, but let me bring that spreadsheet up. So here we have an example to work. Oops. Okay. So we have this pipe network. We have a reservoir over here with an elevation of 132, and all these are in meters. Excuse me. And then pipe 1 coming down to node 1. I put the nodes in brackets, the pipes in parentheses. We have a globe valve up here in our third pipe. And we have another reservoir over here with an elevation of 120. So down here at the bottom, we have all the pipe numbers. We know the pipe diameters. We know the pipe length. We have an assumed friction factor. All right, once again, this has been assumed. We're hoping it's close. Be no different if we didn't know the friction factor. We just put the friction factor equations into this and loop through them as well. Okay. I've added the globe valve, so let's talk about this. Remember, we said that the globe valve adds additional head loss to our system. Now, I would hope that we would know the direction of flow that's going through our globe valve. Okay. But sometimes people do crazy things. I remember I went to a seminar and was listening to a guy present, and he was giving a discussion on pipe networks and transients in them, and talked about this particular city, and it might have been Toledo, Ohio. I can't remember for sure. I think it was somewhere in Ohio. And he said they built this nice new brand new tank, like a 5 million gallon tank, up on a little bit of a hill. And they filled it up. And they noticed about 2 weeks later, because you have to take water samples out of these tanks, especially when they're new, because sometimes you don't get them clean as clean, and you want to make sure that you don't get bacterial growth. And they noticed that the water quality started going bad. This is not good. So they drained the tank, filled it up again. Figured, well, maybe it was just new construction. There's something in there. You know, started monitoring a little closer 1 week. Now they was taking samples more regularly 1 week. They started to go bad again. Well, what's going on? So they drained it, went inside with a pressure washer, sprayed the whole thing down, drained it, filled it back up, thinking we got it this time. Lo and behold, after a short period of time, the water quality went down again. Like, what is going on? So they brought in this guy, you know, who's an expert. Started looking at the system. Turns out that they had a check valve that they had put in, so water wouldn't go back into the tank when it wasn't supposed to. You had a fill line, or the fill line and the drain line for the system was the same thing, and they put the valve in backwards. So it would fill up, but it would never drain. Water would never go back into the system. So it just sat there for, you know, weeks, and it would kind of go bad. Anyway, so one would hope that we know the direction that it's supposed to go when we have valves in our systems, and when we get to pumps, you better know which way it's supposed to go too. But there's been cases where big pumps have been teamed up with little pumps, and water's going backwards to the pump, which, by the way, is not good for pumps, and we'll talk about that. But nonetheless, so we add that globe valve down up there, we bring it down here, and we can calculate a C value for that globe valve. All right. Now I could put those separately into my matrix. When I say separately, they go in the same cell, but I can put, you know, C sub 3 plus C sub 3 globe in the same cell times then Q prime sub 3, the absolute value Q prime, or I can add them together. If the velocity is the same I can add, this is the advantage of turning into the flow rate. If you turn the C value into flow rates, it doesn't matter about the velocity, everything's built into that value. So you can see up here at the top, or when I highlight this, that has the area built into it, so it's type of the flow rate. So now I can just go ahead and add those two C values together. So pipe 3 now has a C value 550 rather than 381 for the pipe and 169 for the globe valve. And this is the minor loss coefficient 8 of that globe valve that I have put into that equation. Okay. All right, everyone feel comfortable with that?
Can you please repeat that again?
Okay, so the globe valve has a minor loss. And I want to convert that minor loss into a coefficient that can then go into my matrix so I can solve for the flow rate. So I join the friction loss and the minor loss together in that C value.
To the friction loss of the C value plus the friction loss of the C globe.
Not the friction, the minor loss of the
I mean,
globe.
the minor loss.
Yes.
Is that all over D squared over 2G
Plus
of the C?
K times 1 over 2G divided by A squared. Yeah,
That one for the C and that one also for the C globe.
correct. Add those two together. Yeah. Yeah. Yeah, okay. Get back here. So now that I have those, I got the C values. Now I can go ahead and construct my equations. And notice I do have the demands over here. Okay. So let's see, do I have? Okay. So I'm going to jump over to the next sheet right here, and I'm going to write then the equations here. Okay, equation 1, equation 2, and I'm going to have to go down through equation 9. Make this up. Oh, wait, there's only 8 pipes in this one, isn't there? I'm jumping back to my example in class. Okay, 8 equations. So my equation, I'm going to first do my continuity equations, right? So I'm going to look at node 1. First off, I guess let me jump back here. We need to put some directions in, don't we? I don't think I have them in on this diagram here. Oh, I do have directions there. I wonder why my directions didn't copy over. Let me go ahead and put them here so I have them in front. You might want to add those directions to those here in class. Okay. So now I can go back to this sheet right here, and for equation 1, I want to write the continuity equation at node 1, right? So using the sign convention that I typically like, flow in is positive, flow out is negative. I'm going to get Q sub 1 minus Q sub 2 minus Q sub 6 equals 0, right? So this is continuity equation. So I'm going to have 6 continuity equations. So I'm going to go to node 2. Node 2 tells me that Q sub 2 minus Q sub 3 minus Q sub 7 equals 0. I'm going to go to node 3, which tells me that Q sub 3 minus Q sub 4 minus Q sub 8 equals 0. All right, go to node 5, which tells me that Q sub 6 plus Q sub 7 minus Q sub 5 equals 0.
You're just writing the equation for the nodes.
I'm writing the equations for the nodes, correct. Now I go to my last node, which is 4, which is going to tell me that Q sub 4 plus Q sub 5 equals 0. Now I've done something wrong to these equations and no one said anything. What have I done wrong, Scott?
Sorry,
What have I done wrong?
Well, we've got two flows going in and no flow going out.
Okay, so what have I missed?
Good at the demand.
Gotta add the demands, yes. So I'm gonna come back up here, and on the demands then, depending on if I wanna put them on the left side or the right side, you guys care? We're gonna do, you know what, we're gonna do the matrix here. So I'm gonna put them on the right side. So the demand is known, and the demand, if I put it on the left side, is going out. So when I move over to the right side, it turns positive, right? Everyone comfortable with that? On the left side, it would be a minus D1 in this first equation. I take that minus over this side, it becomes plus D1. So now this is going to be equal to 0 because there is no demand at node 1. Node 2, I'm going to have 0.04, that's cubic meters per second, so that's why it looks so small. Node 3 is going to be 0.06, so 0.06. I guess I better be a little more formal in my. Okay. At node 4, I'm going to have.
It's actually node 5.
I'm sorry, what?
The equations that you wrote, Q6, Q7 minus Q5 is actually node 5.
Oh, it is. You're right. Thank you. So this is I jumped in my. So node 4 then is going to be.
You just.
Oh, okay. So 0.75. Thank you. And then down here will be the 0.1. All right. Those look correct.
So equation 4. The demand is 0.7.
Extra 0.
Extra 0. Oh, okay. Thank you. All right. I see. All right. I'm like that.
Dr. Bruce,
Yes.
why is, I thought the demand at node 4 is 0.1 in summation?
Say that again.
Equation 4 is actually for node 5, Mark.
Yeah.
Oh, okay.
So let me clean this up again. This is node 1. Oops. Node 2. Node 3. Node 5. This is node 4. I got a little sloppy in almost down. Okay, so now I can write my loop equations, right? So starting with the first loop, once again, clockwise rotation. So C sub 2, I'm just going to write C sub 2 times Q sub 2 squared, write it in this form. And I'm going with the flow. So I'm going to go negative, follow my hydraulic grade line, I'm going with the flow, I'm going down my energy line. And then I get to the next one, which is pipe number 7, going with the flow. So minus C7, oops, C7 times Q 7 squared. And then I'm going to go against, my loop is going against flow in pipe 6, so plus C sub 6 times Q sub 6 raised to the square, and this equals 0. So that's energy loop 1. I go to 2, and I'm going to start with pipe 3, and I'm going with the flow. So minus C sub 3 times Q sub 3 raised to the square. Oops. It's an equation rather than or a label rather than an equation. And I note that in this case, I'm using Q3, the final Q3, the one that has the globe valve with it. And then the next pipeline is pipe 4, and I'm going with the flow there. So C sub 4 times Q sub 4 squared. Going against flow rate in pipe 5, so C sub 5 times Q sub 5 raised to the square. And I'm going against pipe 7, so plus C sub 7 times Q sub 7 raised to the square. And all that has to equal 0. And I do a check here because I know 7 is my common pipe. And in the first loop, it's negative, and the second loop, it's positive, which is as I would expect it. So now I can write my pseudo loop. And I'm going to start over on the, I should have labeled those. I'm going to call this B. Call this one B and this one A. Okay, so the one on the right is B and this one is A. So I'm going to start then with the hydraulic grade line at B. And I'm going to go through pipes 8, 3, 2, and 1. So I'm going against the flow in pipe A, so plus C sub 8 times Q sub 8 squared. That takes me over to pipe 3, so minus now, or plus, because I'm going against that as well. So plus C sub 3 times Q sub 3 raised to the square. The next pipeline is pipe 2, still going against it, so plus C sub 2 times Q sub 2 raised to the square. And I get to pipe 1. And pipe 1, then I'm going against that as well, so plus C sub 1 times Q sub 1 raised to the square, and that has to equal the hydraulic grade line of A. Okay. Now I would note that I could rewrite this equation by taking the hydraulic grade line at B over to the other side and subtracting it. Now that kind of gets it into my matrix form, if you will, where I've got the unknowns on the left-hand side, the known values on the right-hand side.
So what do we call the equation 7? Is that energy loop 2?
Yes, so equation 7 is the energy loop 2, and this equation 3 is going to be the pseudo loop.
No, we always assume the higher one is HDL and the lower is HLA.
No, you don't have to make that assumption. B could be the highest one.
No, we just reverse it, right? The equation.
No, you still write it the same way. If B was higher, the value of B would be higher.
No, I mean, like, you could assume that this is HDL and this HLA.
Yeah, that's just because I labeled the one on the left as A and the other one as B.
No, my question is what happens if you make this HLA and this one HLA? Is that possible or does it don't work right?
It's a direction of what you choose.
Yeah, it doesn't matter if the one on the right was higher in head. Let's say it was 250. It still wouldn't matter. We're going to go clockwise. Once again, that's not so rigid either, but we're going to follow the loop direction. So we're going to follow that loop direction through our system to maintain consistency, that we do everything in the same direction, maintain the same sign conventions. But B could be the higher one.
I got it.
Okay.
Yeah, thank you.
All right, yep. Okay, so now we can come down here and build our matrix. All right. And so we would start off with the first equation, and I know that I have a coefficient of 1 in front of my Q, negative 1 in front of Q2, and then a bunch of zeros. 0, 0, until I get over to Q6, and then I know I have a negative 1 there. And then Q7 is 0, and Q8 is 0, and my B vector is going to be 0 in that case. Okay. The second one is going to be 0, and then I'm going to have 1, negative 1 for Q sub 3, and a bunch of zeros until I get over to 7, and 7 is going to be a negative 1, and 8 is going to be 0, and then my B vector is going to be 4.04. Okay, now you know how to do all the continuity equations. Let's do one of the energy equations. So come down to the first energy equation. Okay, I'm gonna have 0 because I have nothing for pipe 1. And then I'm gonna have negative C sub 2. So I'm gonna have to come up here and grab C sub 2. And I'm gonna get that fixed. I'm gonna multiply that by my guess. In this case, I've put my guesses over here on the left-hand side. So I'm gonna multiply that by the absolute value, thank you. Yeah, I almost forgot there. The absolute value of Q sub 2. And that is my whole value right there. Right? And I go to C sub 3. And C sub 3 is 0. And I go to C sub 4 and it's 0. And I go to C sub 5 is 0. And C sub 6 now is a positive value. So I'm going to come over here and grab C sub 6, make that absolute, times then the absolute value of Q sub 6. And there's my value there. And then I have Q sub 7, so minus, I don't know why I lost my 7 up there on pipe number, but C sub 7 times then Q sub 7, absolute value, absolute value Q sub 7, and that one is complete.
So, Dr. Bruce,
Uh-huh.
there's an assumption that Q prime is absolute value of Q.
Yes, Q primes are old value, and we're going to take the absolute value of it to maintain the direction. Okay, now I'm going to come down to the pseudo loop, because once again, this next energy equation is the same thing. I mean, not the exact same thing, it's the same procedure, right? I'm out of time here, so really fast, the pseudo loop then. Going across there, I have C sub 1, so I'm going to do my C sub 1 as positive, times then the absolute value of Q sub 1. And you know, it's going to be the same thing all the way across until, note that over here on the hydraulic grade line, I'm going to put the hydraulic grade line of A in, which is 132, minus the hydraulic grade line of B, which is 120. And so once I fill all those cells in now with the appropriate zeros and everything else, now I can use the same methods that we used for the 3 reservoir problem to solve this pipe network. Okay. So I'm going to give you a homework problem, and what we'll be due on Tuesday is the equations, the handwritten equations, and I'll give you extra time. What will be due on Wednesday is the matrix method, the circular matrix, the modification, and the solver on that pipe network. Okay,
The one doing is
just the handwritten equations like what's due today, but it'll be on a new problem, a new pipe network. Okay, that'll have some fixed grade nodes, and then you'll have extra time to solve that. And on Monday, if you get a good start on it, Monday we can kind of look at it a little bit more. Have a great day. Have a wonderful weekend, and we'll see you on Monday.